Hello, my name is Carlos Mateo, and today I will be presenting on fully homomorphic encryption. To introduce the topic, we must first discuss cryptography, which is the transmission of secret information from one person to another over a medium. This is possible through the use of ciphers, which are able to convert plain text into ciphertext, which is just an encrypted version of the data. This day and age, in 2019, there is an increasing number of devices that have to that are accessing the internet, and most of these devices are unable to process their data locally. Thus, they transfer their data to a third party for processing. Now, sometimes the data in question is either sensitive or confidential, and thus you would not like outside individuals to see what your data entails. Thus, the best resolution so far for this issue is homomorphic encryption, which is a type of encryption that allows for computations to be performed on encrypted data. Now to describe homomorphic encryption, it's basically a form of encryption where you can perform operations on encrypted text, so the ciphertext, and get an encrypted result, which, when decrypted, would be the same result you would get if you were to perform such operations on the original plain text. So to illustrate this, we have a little figure on the bottom left to introduce the jewelry shop problem. Imagine a shop owner would like her or his employees to create necklaces and rings from precious raw materials such as gold and diamonds. Now, the only issue is that the owner does not trust his workers, and thus is concerned about theft. In order to not be worried about such a thing, we compare the homomorphic encryption to the creation of a glove box, a transparent glove box. In this transparent glove box, the only person with access inside is the owner, who has a key to the glove box, while all the employees use the gloves in order to use the tools and materials inside the glove box to create these arrangements. In this example, the tools and the glove box represents the encrypted data, so the data is not physically available to the employees, but is visually available. And inside the glove box are the raw tools, which is your initial data, and the tools are the actual data encryption. Now, when the necklaces and the rings in this example, which are retrieved by the owner with her key, is the final computation from the encrypted text, basically the computation that is desired. Now, there are a few types of homomorphic encryption. There's partially homomorphic encryption, where the crypto system can perform addition or subtraction, but not at the same time. Somewhat more homomorphic encryption, which is when a system can perform addition or subtraction, but addition and subtraction, but only for a limited amount of times, a finite number of times. While fully homomorphic encryption allows for unlimited multiplication and addition operations to occur, thus, being revolutionary in the field of cryptography. Why, do you ask? Well, this implies that fully homomorphic encryption can provide third parties with data where the input is still encrypted, but the third party is still able to perform calculations and the desired result without knowing the details. So a few applications of fully homomorphic encryption. The main one is cloud-based data analytics. So imagine you're an individual who does not have the tools needed in order to perform calculations on a certain data set. But you would also like this data set to remain private. Now, what you would do is encrypt the data set, then send it over to a third-party cloud program, which will then perform the calculations on the encrypted text that you desire. It will then send back the encrypted text, and you will decrypt it in order to retrieve the desired result of the calculation. This works with a group setting too. Imagine there's an analyst or a epidemiologist who would like to gather the data, would like to use the data gathered by other epidemiologists in order to create a statistical analysis. Now, what you would do is the analyst would give their key to all of the different scientists in question so that they can upload their data using that key. This way, the analyst will never know specifics about the data upload into the cloud. The cloud then performs the directed statistical analysis, and then the analyst would just need to use her key in order to retrieve the desired result. Other applications for fully homomorphic encryption is the private database query system. In this system, the user would enter a question into the search engine, and the search engine would not reveal any details about the individual components of that engine, as well as the user will not, the system will not embroach or understand fully the reason for the user asking that said question. Targeted advertising is another field. Imagine if you're a part of a company who would like to target their advertising to a certain consumer. These companies can use an individual's public key in order to retrieve what would be private, sensitive data, such as emails, texts, web browsing, details in all of these. They can encrypt it, then not know where it came from or the details, but know that they reveal a certain preference for certain items. That can then be calculated like in a cloud system, and then returned to the company to determine what particular consumers would like a particular product. Now, a few hard mathematical problems involved in fully homomorphic encryption. First is the lattice problem. Since the basis of most primary attacks on a fully homomorphic encryption crypto systems is they are based on a lattice algorithm. Now, as pictured on the right, here's an example of a lattice. Because of the fact that these attacks are based on this algorithm, there are a few underlying problems under this umbrella term. For example, the closest vector problem. The closest vector problem is concerned with a vector t and a lattice in question. Now, the question is to determine whether that vector t is a part of the lattice system, like a multiple or included in the system, or if it is an individual vector that is just very close to the lattice in question. If it is the latter, where it is not part of the lattice system, it can be used to create a valid secret key to convert ciphertext. However, if it is actually part of the lattice system, it would not be compatible with the secret key in question, would not be compatible with the plain text that we are dealing with. So basically with this vector problem, you could determine whether a key will be valid for ciphertext, for creating ciphertext. The shortest vector problem is similar, where shortest vector problem is similar, where you are looking for the shortest non-zero vector in a particular lattice. To continue, we have the sparse vector subset sum problem, and in order to explain this, we have to explain the concept of bootstrapping. Now, when we convert, data is converted into circuits, and in these, which allows us to represent in fully homomorphic encryption, we deal with circuits. Our data is converted into circuits, which is easily understandable, and but the problem with homomorphic calculations is that the noise that is attached to certain data to locate it better actually grows as these calculations are performed. In order to avoid this, we must re-encrypt. We must do a re-encryption where we convert that decryption into a circuit. We run a public key encrypted with a secret key through that circuit, and in this way we create a ciphertext that is identical to that of the plain text, only it now does not have any noise. So this allows us to circumvent the problem of this system being so malleable. The crypto system depends on that random set S, a subset T, and a secret key vector. So we have a set of m n-bit numbers. We have to determine whether that set is random, whether there's a subset T that is not random, that whose elements can add up to a secret key vector. Basically, these elements determine the level of security we're going to be dealing with. Now, if it is completely random, but it's so small that the subset T is unique, it's a unique answer, then you're going to be very susceptible to lattice reduction algorithm attacks. Versus if the random set S is sufficiently large to run on polynomial time, and the subset T is uncountably infinite, this means that lattice-based reduction algorithms will break down, will not be effective, for example, in attacking the system, and also if the subset T does exist and is sufficiently large, then it means the system will be susceptible to lattice reduction algorithms in exponential time. So basically these components and their existence, the subset T, the random set, and the secret key vector, determine to what extent our fully homomorphic crypto system is secure. Now, the required computations for this algorithm involve converting our data into circuits, whether it be Boolean circuits or arithmetic circuits. In Boolean circuits, we deal with AND or OR gates. So there are two gates that, when homomorphically evaluated, can result in any computation we desire. So it's very convenient as in that aspect, but for us to actually evaluate an algorithm in question, we would have to convert our entire algorithm into a Boolean circuit, which means only using addition, multiplication, and omitting any conditionals or loops in our algorithm. Arithmetic circuits, on the other hand, can be further divided into modular or approximate number arithmetic. In modular arithmetic, we use data is represented in modulo form and versus approximate number arithmetic, where is represented by real numbers. While modular arithmetic is better with high precision integer arithmetic, and also better with faster scalar multiplication, approximate number arithmetic is actually better in regards to multiplicative inversion and discrete Fourier transformation. Boolean circuit exhibits faster bootstrapping, but it actually requires bootstrapping, unlike the arithmetic circuits, because of their layered design, their multi-level design, they require less need for bootstrapping. The implementation results are summarized in this figure right here. These systems are represented by different colored dots. So we have the Intel Xeon E5450 quad-core processor. That is represented by the blue, and that is the main implementation we are looking at. As you can see, the D is the bottom axis, and that refers to the dimensions of the lattice in question. And as the dimensions increase, obviously the implementation time increases. But we're showing the runtime of 4 different implementations in the actual encryption crypto system. The fastest would be decrypt, which operates at an order of 10 to the negative 2 seconds, followed by encrypt, whose runtime is in seconds, and key generation and re-encryption, which are the 2 implementations that take the longest. Both reside somewhere between 10 and 100 milliseconds runtime. Also, this figure shows us a particular example on an Intel Core Duos E6600 processor. We can see that if we are not taking into account bit representation and instead large messaging, the performance drastically improves as we convert our data from bits to large messages. So, as a conclusion, fully homomorphic encryption represented a breakthrough in field of cryptography because of it's considered the holy grail of cryptography still because of its many implications and applications in different fields, not just cryptography, but also management sciences as well. Now, even though it would be ideal to use, current fully homomorphic encryption schemes are not yet practical on a large scale due to limited computational performance. This is mainly due to the re-encryption and how time-consuming this implementation is in order to reduce noise via bootstrapping. For the meantime, these fully homomorphic encryption schemes must be developed for specific applications and with specific, according to which specific results are desired. We have yet to form a universal version of this encryption, and further research is needed in order to do so. These are my references. Thank you very much.